Thank you for tuning in. I'm Suhail Alnahari, and this is Active Learning for Object Detection and Segmentation, part of the Data Science Capstone Project Fair at the University of Minnesota. Let's get started. I'm going to start by briefly outlining what this video will be about. First, I'll explain what active learning is. Then, I'll give reasons why active learning is necessary. After that, I'll discuss Mask RCNN, which is an object detection and segmentation algorithm, and propose an active learning solution for it. Then, I'll provide some results for the solution under a multi-class classification setting and provide some benchmarks. This is still a work in progress, so before we end here, I'll explain the work that's left. By definition, active learning, which is similar to optimal experimental design and statistics, is a special case of machine learning in which a learning algorithm can interactively query a user, which is sometimes called the teacher or an oracle, to label new data points with the desired outputs. I started working on this project after joining Zooniverse. Zooniverse is a crowdsourcing organization specialized in supplying scientists with labeled datasets for research purposes. Zooniverse has many experts that volunteer to label computer vision datasets. As you can see, with each passing year, more and more projects are created that need thousands of classifications. However, volunteers aren't acquired at the same rate, so active learning is necessary for a more efficient and a faster labeled data collection process. One example of the projects at Zooniverse is the University of Wyoming Raccoon Project. The project's goal is instance segmentation, which I'll be explaining in the next slide. Object detection algorithms require large datasets. The project was published 3 months ago, and as you can see, is 63% to completion. However, using active learning, volunteers will only label frames that help model performance, which will decrease the amount of data necessary for labeling, as some frames can be similar to each other. From the examples, you can understand what instance segmentation means, which is not only identifying the object type and its shape, but also identifying which unique object it is. You can also see the kind of images volunteers at Zooniverse label. Mask RCNN is conceptually simple, if you know how fast RCNN works. It's simply a faster RCNN plus another fully convolutional network, which is connected to the region proposal network that predicts the output segmentation, also known as object mask. It's based on parallel prediction of object masks, classes, and bounding boxes. The loss function for mask RCNN is simply the sum of classification loss, bounding box loss, and mask loss. Because existing methods are hand-designed for specific problems such as classification, they aren't well suited to more complex tasks such as image segmentation based on what you see here. In this project, our main goal is to develop an active learning paradigm that is flexible enough to handle tasks such as image segmentation of raccoons. So we need to develop a method that works to choose data points by directly estimating the loss of our model. For simplicity, I chose to experiment under a classification setting. Let's assume that the cross entropy for a data point of a neural network W is given by L1 in blue. The value of L1 makes the network adjust its weights to minimize L1 in the next backpropagation. L1 is unknown, but if we have a good estimate of L1, we could choose samples that have the highest estimated loss that the network W1 will have, assuming that there are no false outliers. This means that the model will have more samples that are likely to be incorrectly classified, which will help during training. However, we need our estimated loss to be more general. Otherwise, we will overfit on the performance of model W1. So if we have capital M fixed models, and we take their average estimated loss, then with more data points, we will obtain the true average model loss for each data point. However, we don't have the computational resources to obtain an ensemble of neural networks. So having m equals 1 is sufficient if we reinitialize the model after each new acquisition of the training data. With that, here are some results for this procedure. Feel free to pause the video to read the configuration of the experiment. As you can see, the performance of the new solution is higher than random, but close to BALD, which is the active learning algorithm most recently used at Zooniverse that is specific to multi-class classification. The solution obtained this result much faster than BALD, since BALD requires running through the unlabeled set multiple times to obtain a prediction. Since the experiment was only done for a small portion of the fashion image data set because of the computation cost, the proposed solution might not have been as effective since estimators achieve better accuracy with more data. Another scenario that was tested was if we use an imbalanced dataset, which is common. Then, as you can see, random performs worse as it picks up more samples from the dominant class more often. On the other hand, the proposed solution performs well in obtaining objects of the imbalanced classes more frequently. To summarize, active learning promotes efficient crowdsourcing, requires capturing model loss for not only classification, but object detection and segmentation, and is most effective for unlabeled imbalanced datasets. My future work consists of estimating the loss function for mask RCNN, using more complex data sets and perhaps models, and studying model architecture for the loss estimator. Here's a list of references I used for this video. Thank you for watching.